Conway's Game of Life. What would it look like in a parallel universe? Not the exact same universe, but a parallel universe that's a little different. Well, we're going to look at that, and we're going to use that as an example to look at two programming tools called lookup tables, and then a small micro mini language. So let's go ahead and bring up our nested loop version of our Game of Life, and we're going to see the kernel of how the rules for this universe existed. Conway actually tried several different sets of rules, and he wanted, he's an intelligent man, and he wanted to come up with a way to make a life that had a lot of creativity in it, that had a lot of interesting things happen, and it didn't just fill up or die off too quickly in either way. So the algorithm we have in our nested loop example has several things going in it. We have our two nested loops that visit every cell. Then for each cell, we're calculating how many neighbors it has. And then we're actually using the rules, sort of the kernel of this algorithm that says for each cell, is that cell going to stay alive or stay up, or is it going to go falling asleep and die? So the rules are in there. So we have three different things happening all in this piece of code. And whenever you have too many things going in, it's okay here, but if I start to want to add variation, like maybe I want to make an if statement that says, well, in universe 1, we're going to use rules A. And in universe 2, we're going to use rules B. Well, if I start putting logic inside of this, the code would be even harder to read. So that's where there's other tools for how you want to separate the two pieces of code. We could certainly pack this in a function, but this is an ideal example of somewhere where we can use something called a lookup table. So we're going to take that kernel of this function here, where we're doing the neighbors and the cells right there, and I'm going to break that out, and we're going to pull it aside and look at it a little more detailed. So the inline logic we're dealing with now, we have count how many neighbors. That's got pulled out into another function. That's nice. And if it's currently alive, then we're going to stay alive if it's 2 or 3. But if it's dormant, then only if it's n equals 3 will it wake up, come to life. Now we could do this in another way. We could have a lookup table. So the answers let's take that second part here, where I have the rules for when I want to wake up. In this case here, I have wake up, and each element of this list is an answer based upon how many neighbors it has. So for 0, it's false, 1, it's false, 2, it's false, but for 3, the answer is true. And then the rest of the over here are false too. So 3 is the only one that returns true. So that's sort of another implementation of the saying is n equals to 3. Now, the difference is, if we want to go in here and add logic or change it up, so instead of it's n equals 3, maybe it's n equals 4. Maybe it's n equals 3 or 4. Each time I want to change that with the code as it's written in the top, would require me to stop the program, go type in the new equation, and then run the code again. If I have it done as this list, I can just switch out which list I'm using. Which list I use for the wake up rules and which ones I use for the stay up rules. And once I have those lists, now the logic in that kernel will turn into, well, still we find the number of neighbors, and then we're going to set the side of the answer for our current state into a variable up. And now that if then else with all the different logic in it turns into one line. So it's if we're not up, and we should wake up based upon the number of neighbors, or we are up and we should stay up based on the number of neighbors. And that's all one logical expression, and we're going to return the new state, and that will get put back into the next generation, the array. So for it being number 4, we're going to say if it's not up, number 3, and we're going to wake up based upon 3 neighbors, that would be true. And with shortcut evaluation, the computer will actually just stop right there and return, says, hey, this is an or statement, if A or B. If A is true, I don't have to ask B, and it will just return that back. So this is just as efficient as the if then else that's used above. So now we have the idea of how to make the table. Let's look a little bit more at why you would do that. Well, the general element of when you use a lookup table is when you have some function of n, where function is perhaps complex, perhaps just code you don't want to pull into where the algorithm's being used. You might not even know what it is. But And the key other part here is that there are only a few number of ends, relatively few number of ends. And so in our case here for our 3x3 grid, and I'll go ahead and just consider the whole 3x3 grid, even though the center frequently doesn't factor into it, there's at most 9. There's almost 9 answers. So we can figure out what the answer is for 0, so f of 0 through f of 8, which would be 9 different answers. And now it's easy to just see that, hey, I could just change this table. I could change it from having a true in one cell versus true in a different cell. So in short, I can look at here. Oh, yeah, look at this one. So what are kind of places that happened? Well, first of all, it's kind of interesting that for centuries, all your trig tables, that's the way they were done. I mean, centuries all the way back into the 70s and honestly still into the 80s and 90s, there's still big books out there with all your math and trig functions. I mean, you can still find them in the half-price bookstore. And then tax rules. Tax rules still use them. The government will publish and say this is what the tax rate is for different values. And even though the functions are known, there's things like rounding. And so the government says this is the way it should be rounded. Another area is just in the world of physical instrumentation where we're doing sensors. And so you have something that's perhaps measuring temperature. The raw voltages you get off of a transducer can be very hard to map in a mathematical function. So you simply map it and you calibrate it and you say, okay, this is what 98 degrees looks like. This is what 99 degrees. This is what 100 degrees looks like. And as you do that, you just put in the table and perhaps you'll interpolate between them. Another area is where you just want the functions to happen consistently fast. So in a car system, in engine control units, they're frequently using lookup tables so they can map RPMs and oxygen levels and nitrogen levels and figure out what the fuel is supposed to do, because that's being done thousands, if not tens of thousands of times a second as it's figuring those out. And another case is the algorithms might be known, but they don't want that algorithm to go with the hardware or to go with the source code. So they will just put the lookup tables for the values that are there. And when something else changes about the system, they can go to their equations and come up with new ones, but it's proprietary information. So that's a few. There's numerous cases. Now in our code, once we have this table, what looked like that simple greater than or equal to 2, less than or equal to 3 turns into this. So unfortunately, that's not a step in the direction that made sense. So these tables can look confusing. And worse than that, when I did the check, then it says, no, you need spaces in there. But if I had the spaces, then the lines became too long. It's like, but this was not heading in the right direction. So another approach, or one to add on top of this one, is to actually make a language for defining our tables. And so here you're seeing this little language with these little strings, and the underscores equate to falses, and the X's equate to trues. So the wake up, basically on here, I'm seeing, looking at this one right there, says, if I have 3 neighbors, exactly 3 neighbors, I'll come to life. I'll wake up. And so I just have that 1X. And so this becomes a really concise way to express it. It's very easy to read the code and see what's intended there. I don't have to look at greater than, less thans, and ands and ors. It just shows up right off the bat. Now to make that, it turned out that was basically a 1-line piece of code. And we're using list comprehension. So we're going to make a list. That's the part right here. And this is the list comprehension example. So it says for B in rule, so the B in this case is going to be a character because rule is passed as a string. So for each character, the list element will be a logical condition, so true or false, based upon whether or not B is the underscore. So that's a little shortcut. I use capital X's because they're really easy to see, but the way it's written, it wouldn't matter what letter. So this is then what we see in the source code when we're editing it, we're looking at it. But at runtime, we're actually getting the implementation that's efficient for the computer to use. So mixing them together, we have a tool for building the lookup table, and then we have the table that's actually used at runtime. So let's go and look at see how that code all ended up. So this was the nested loops. We did have a version that has the rules set up originally like this, but it had 2 global rules. So when I wanted to go to the multi-rule version, Now we actually have a global that's the array of all the rules. And I kind of used the keyboard, what was logical for the keyboard, so we stuck 0 as a kind of a special one. But 1 is the original rule game. So that's the one that's on the left edge of your keyboard. So this is going to be the standard rule. Then you can see over here, we've added a state where there's one more state where something will stay awake. So we can presume that that's going to last a little longer. This case, I actually got rid of one of the states that causes it to stay. So see how that's working. Now we just shifted it. We have 2 more on this side. And here we've added another one that'll, 2 states will cause it to wake up. So I'm wondering if that's going to grow real fast. 7 has a lot of states, which will cause cells to stay alive. And Control X here. So you could just add to you could explore the space yourself. But here's just a few of them. So let's go ahead and see how this works. So we're running this code, and this is rule 1. So this is the game as we're familiar with it. I can clear the screen, put random numbers. Each time you see some of those same characteristic things, like the blinkers are the ones that stay still. Oh, they got eaten there. Okay. So that was rule 1. Let's go ahead and switch to rule 2. That was the one where things tended to stay alive a little longer. In this case, it's just growing. It's the blob. It's taking over all the space. Now we see inside of there's still some activity going that hasn't settled down to a idle state. And so this becomes a mathematical question. It seems like there's fewer and fewer as things are kind of morphing down. Now you'll see there are patterns in here. I can still see there's variations of the blinkers, like that one there. And this thing here, yeah, right there. So those look like they'll last that way forever. And I could go in, I could click in a cell, but you can see that this doesn't lend itself to life very much. Things just end up becoming dormant really quickly. So this parallel universe doesn't look all that exciting. I wouldn't want to be there. If I was, I don't think I would be alive. All right, that was 2. Let's go to rule 3. Rule 3, things dissolve really fast. Though there are a few of these own little blinker patterns there. Like these guys, these actually have a few states they go through, so it's not just on and off. It just kind of keeps rotating around. This one runs in place. It doesn't matter if I go make random. We're constantly seeing it just break down into just a few patterns. So universe number 3, not so fun either. See 4, it's even crazier. Now 4 is an interesting one. Most things don't lie, but a few things can, and if they take root, then they'll just grow. That reminds me of our virus. And I got 5, and 5 is even crazier. Let's see, random. They grow fast like that. And I think 6, random. And 7 is even quicker. 7 is super dormant. I mean, there's not much that ever goes on here other than a few blinks. Now I'm going to pause here and I'm going to clear. This is an interesting one on 7. See, if I go and run, it just goes away. 1 dot. I do 2 dots next to each other. Go ahead and run. It's like the big boom in that universe there. Okay, it just takes up. But again, it's not a very interesting life. It's just all rigid and fixed. So not the kind of universe I'd want to live in. So short, we've implemented a handful of rules, and we used lookup tables to implement them. And because we have them done as a lookup table, when I change one of those keys, the only thing that's happening is I'm changing what rule we want to use. And so we have a table that has 10 different sets. And when I set that one variable, these are the tables to use, then the internal algorithm will do everything based upon that one rule. And we're using the table to look it up. Another example is that thing, instead of pointing to a list, could point to a function that we would call. That's another case for another day. All right, blessings to you all. Amen. Bye. Oh, wait, hold on. Yeah, I need this. How can I not do that? All right, there we are. The game of life in parallel universes. CS Foundations with Paul Austin. Take care.